This lesson is over composition of functions. The composition of functions f circle g is the composition of f and g, defined as f composed of g, which equals f of g of x, where x is the domain of g and g of x is the domain of f. This is a new notation that is f circle g of x. That is not multiplication. Now, because this is a new symbol, I want you to know how to read this. You can read this as f composed of g. You can read it as the composition of f and g. Or you can read it as f circle g. But in other words, what this means is we are stuffing a function inside another function. Let's look at an example. Example 1. Let f of x equal 2x minus 5 and g of x equals x squared minus 3x plus 8. For A, it says find f composed of g of x. Well, anytime you see this written as a composition with a circle, your first step is to rewrite this. And so it would look like this. When we read the problem from left to right, what is the first function we see? Well, it's the f function. And then as we look on the inside, what function do we see? G of x. So what we do is we start on the inside. G of x is what we see, but we know g of x is the same thing as x squared minus 3x plus 8. We keep everything else exactly as we see it. So the f is still on the outside. Now notice we have grouping symbols. Can you do anything inside the grouping? No. Any exponents? No. How about multiplication or division? No. Subtraction, addition? No. Which means we no longer look on the inside of the grouping, we now look on the outside. And on the outside you see f. That means we are going to look at the f function only. The f function is 2x minus 5. But every time you see x, you put parentheses. Now, the value that goes inside the parentheses is what we see. That's where the g function will go. So we plug the g function, or x squared minus 3x plus 8, inside the f function. From here, we do order of operations again. GEMS. Can you do anything inside the grouping? No. Exponents? No. Multiplication, division? Yes. We now need to distribute the 2. 2 times x squared, 2 times negative 3x, and 2 times 8 will give you 2x squared minus 6x plus 16, and then we still have that minus 5. Since there's no more multiplication division, we're ready for subtraction addition. And notice you do have some like terms, your constants. It all combines to give you 2x squared minus 6x plus 11, and that would be your final answer. Now for part B, it's reversing the order. This time we are looking for g composed of f. Now, anytime you see that circle, that composition, you have to take the time to rewrite it. As we read it from left to right, the first function we see is the g function. And on the inside, we see the f function. And so we always start inside the grouping symbols, and inside we see f of x. Well, f of x is the same thing as 2x minus 5. And we keep everything on the outside exactly as we see it. Now in the grouping, there's nothing we can do to 2x minus 5, so we look to the outside, which is where we see the g. That means looking at the g function, every time you see x, put parentheses. And so it will look like something squared minus 3 times something plus 8. Now, what value do we plug in? Well, this is where we plug in the f function, which is 2x minus 5 every time you see x. From here, we now follow GEMS. There's nothing we can do inside the grouping. We do have exponents. Notice 2x minus 5 squared really means 2x minus 5 times 2x minus 5, and everything else stays the same. Now 2x minus 5 times 2x minus 5, you will need to distribute that, and you should find 4x squared minus 10x plus 25, and then everything else stays the same. Do we have any more multiplication division? And we do. Notice we have a negative 3 touching the parenthesis. And if we distribute negative 3 times 2x, negative 3 times negative 5, it does give us negative 6x plus 15, and everything else stays the same. There's no more multiplication division, so now we're ready for subtraction and addition, and so we look for like terms. For x squareds, I only have 4x squared, so that will remain. Now I look for terms that have x's only, and we have a negative 10x, negative 10x, and negative 6x, which combines to give us negative 26x. Now we look for constants, or the plain numbers. We have 25 plus 15 plus 8, which combines to give us 48. So our final answer is 4x squared minus 26x plus 48. Example 2, let f of x equal 3x plus 1 and g of x equals x squared minus 2x minus 6. For part A, it wants us to find f composed of g of the value negative 1. Now notice we see that circle, that composition, so we have to take the time to rewrite this. Reading from left to right, the first function we see is the f function, and then inside we see the g function, but this time we're given a value, and that value is negative 1. So we rewrite it as such. From here, we follow GEMS. We start on the inside, and we can do nothing to negative 1, so we zoom out just a little bit. Now we see g of negative 1. Well, g of negative 1 means only looking at the g function. Every time you see x, you plug in a value. Well, your g function is something squared minus 2 times something minus 6. So now that we have the g function, we now plug in the value, which in this case would be negative 1. And then we keep the f function on the outside, like a tag along. Now on the inside we have all these values, which means we must follow GEMS. Notice we have no grouping, but we do have exponents. Negative 1 squared means negative 1 times negative 1, which gives us positive 1, and everything else stays the same. There's no other exponents, but there is multiplication. We have a negative 2 touching the parenthesis, so negative 2 times negative 1 is a positive 2, and everything else stays the same. There's no more multiplication division, so we move on to subtraction addition. we know 1 plus 2 is 3, and 3 minus that 6 is negative 3. And so inside, there's nothing else we can do. We have simplified it and we have the value negative 3. But we're not done, because now we zoom out completely and we see we still have a function value, the f function. So what this means, looking at the f function, every time you see x, you put parentheses. So it becomes 3 times something plus 1. Now, what value do we plug in? According to the notation, it says f of negative 3. That means using the f function, plug in the value negative 3. Once the value is plugged in, again you follow GEMS. First thing we can do would be the multiplication. 3 times negative 3 is negative 9. And then we have the addition subtraction, and we know negative 9 plus 1 would give us negative 8. And that would be your answer. For part B, it says find G composed of f of negative 2. Again, anytime you see the composition or that circle, you do need to take the time to rewrite it. The first function we see from left to right is the G function. Next we see the f function, and then we see the value of negative 2. And so it would be written as such. Now, we always start in the middle and work our way from the inside out. There's nothing we can do inside the innermost parentheses because all we see is negative 2. So we zoom out to the next parentheses. This time we see f of negative 2. Well, f of negative 2 means look at the f function only, and every time you see x, put parentheses, which becomes 3 times something plus 1. Well, what is the value we plug in? Negative 2. And everything else stays the same, meaning the G function on the outside is following along with us. Now, still looking, since we've plugged in the value of negative 2, we follow GEMS. We have no grouping, no exponents, but we do have multiplication division. 3 times negative 2 is negative 6. Everything else stays the same. No more multiplication division, so we move on to subtraction addition, and negative 6 plus 1 is negative 5. Now there's nothing else we can do inside the grouping symbol, so now we look at the problem as a whole. And it says G composed of negative 5, or G of negative 5. That means the G function with the value of negative 5 plugged into every time you see x. And so we rewrite the G function with parentheses and carefully plug in negative 5 every time you saw x. Once negative 5 is substituted in, we follow GEMS. There's no grouping, but we do have an exponent. Negative 5 squared means negative 5 times negative 5, which we know is 25, and everything else stays the same. There's no other exponents, so we move on to multiplication division. Notice we have a negative 2 touching the parenthesis, so negative 2 times negative 5 creates a positive 10, and everything else stays the same. There's no more multiplication division, so we move on to subtraction addition in order from left to right. And we know 25 plus 10 is 35, and then we keep the minus 6. And then the last step, 35 minus 6 is 29, and that is your final answer. Example 3, let f of x equal negative 5x minus 1 and g of x equals x squared minus 3. For part A, f composed of g of x. This is your try it problem. Let's see how you did. Hopefully you found f composed of g to come up with negative 5x squared plus 14. Part B. Find g composed of f. Again, this is your try it problem. Hopefully you found g composed of f to equal 25x squared plus 10x minus 2. Part C. Find f composed of g of the value negative 7. Again, this is your try it problem. Hopefully you found f composed of g of negative 7 to equal negative 231. Example 4. Given f of x equals 2 all over 1 minus 7x, g of x equals 1 over x. Find f composed of g, g composed of f, and their domains. So, the first part we will look for is f composed of g, which remember means we need to take the time to rewrite this. And when we do so, we have f composed of g of x. Like before, we start on the inside, and notice on the inside we see g of x, and we know the g function is represented by 1 over x. Now, here's the new part to this problem. It's not just asking for f composed of g, it's asking for f composed of g and their domain. So, we first must check. This is our first check for domain number 1. When you introduce a function, you have to check for its domain, which means radicals and fractions. Now notice, do we have a radical? No. Do we have a fraction? Yes. And since we have a variable in the denominator of that fraction, we must take the denominator automatically, whatever it is, and say it cannot equal 0. In this case, our denominator is x, which tells us x cannot equal 0. So we've already removed 0 from the domain. Now we can continue finding the composition. So f of 1 over x means now we're going to look at the f function, which is 2 all over 1 minus 7x. But every time you see x, we now plug in the value 1 over x. And so we have this negative 7 touching this 1 over x. Because 1 over x is a fraction, we make 7 into a fraction as 7 over 1, and we multiply the two fractions. When we do that, our now function looks like 2 all over 1 minus 7 over x. Now if you look at that, that looks pretty messy. So what we want to do is, instead of writing this division vertically, we want to write the division horizontally, which means I want to write it as 2, which is my numerator, divided by, instead of that fraction bar, the denominator, which was 1 minus 7 over x. From here, we now follow GEMS. I cannot do anything inside the first grouping because it is just a 2. But the second grouping, I have a 1 minus 7 over x. Well, because 7 over x is a fraction, I need to make 1 into a fraction. And to do that, I would simply place 1 over 1. Now, I have 1 over 1 minus 7 over x. Because I'm being asked to subtract two fractions, I need a common denominator. and in this case my common denominator would be x. So I would multiply 1 over 1 times x over x. So now my problem reads 2 divided by x over x minus 7 over x. Notice my fractions now have a common denominator, so now I can do addition or subtraction. And since my common denominator is x, I keep the denominator of x and I subtract my numerators. So now my problem is 2 divided by x minus 7 all over x. Notice there's nothing else I can do within that second grouping symbol. So we're done with grouping symbols for gems. We move on to exponents, but there is none. So again, we're looking at the problem as a whole. Since there's no exponents, we move on to multiplication division. Now we're going to take care of that division symbol. Because x minus 7 over x is a fraction, I need 2 to be a fraction, which means I simply write it as 2 over 1. And whenever we're dividing fractions, we multiply by its reciprocal. So we now have 2 over 1 times, now when I flip the second fraction, it becomes x all over x minus 7. Now we are being asked to multiply two fractions, and when you multiply two fractions, you multiply top times top, bottom times bottom. And so we find the result to be 2x all over x minus 7. From here, we cannot reduce, so this would be your final answer. So we have finished the composition of the two functions, but we're not quite done with their domain. We did our first domain check when we plugged in our first function. Now comes domain check number 2. And since it's asking for domain, we look, do we have a radical? No. Do we have a fraction? Yes. Do we have a variable in the denominator of that fraction? Yes. And so we know the denominator, whatever it is, cannot equal 0. So we have x minus 7 cannot equal 0. And so to solve for x, we would add 7 to both sides, and we find x cannot equal 7. So we've done check for domain number 1 and check number 2. We are now ready to find the domain of the overall problem. And the best way to do that is to look at the number line. Domain check number 1 says x cannot equal 0. So we find 0 on the number line and we put an open circle. So we have removed 0 from the domain. Now we look at domain check number 2, and it says x cannot equal 7. So we need to put an open circle at 7 and remove 7 from the domain. Since we've removed both of the numbers that would be issues, that means we can keep every other number. So I can keep the numbers to the left of 0, the numbers between 0 and 7, and the numbers to the right of 7. And since I can see the number line, I can now write my domain in interval notation. It would be negative infinity to 0, parenthesis, union, parenthesis, 0, 7, parenthesis, union, parenthesis, 7, infinity. Continuing the same problem, now this time we are going to look at G composed of F. So again, because you see the circle, the composition, that means we need to take the time to rewrite this as G composed of f of x. Just like previous problems, we start on the inside. this case the inside function is f of x, or 2 all over 1 minus 7x. Now since this problem is asking us to find their domains, we have to check. As soon as you introduce a function, you have to check the domain. And so we look, do we have a radical? No. Do we have a fraction? Yes. Do we have a variable in the denominator of that fraction? Yes. Which means we take whatever the denominator happens to be and say it cannot equal 0. So for us, that is 1 minus 7x cannot equal 0. And so we need to solve for x. Our first step would be to subtract 1 on both sides, which gives us negative 7x cannot equal negative 1. From here, we need to divide both the left side and the right side by negative 7, which gives us positive x cannot equal a positive 1/7. Now that we've isolated and solved for x, we now know that the value 1/7 cannot be part of the domain. Now we can continue with the composition. So the composition is g with the value of 2 all over 1 minus 7x. Since g is on the outside, that means we write the g function, but every time you see x, you put parentheses. Well, the g function is 1 over x. For us, that's 1 over something. And the value we plug in for that something is the f function, or 2 all over 1 minus 7x. Now look at that. We have a fraction inside a fraction. When that happens, you need to take the time to rewrite this division in a horizontal manner, which means we would rewrite it as 1 divided by 2 all over 1 minus 7x. Now, because 2 over 1 minus 7x is a fraction, we need to write 1 as a fraction. But we know anytime you're dividing two fractions, you multiply by the reciprocal of the second fraction. And when we rewrite this, it becomes 1 over 1 times the reciprocal, or the flipped version, which now becomes 1 minus 7x all over 2. Since we are now multiplying two fractions, remember we multiply top times top, bottom times bottom, which gives us 1 minus 7x all over 2, and that is your result of the composition. Now, because we have the end result of the composition, we now need to check our domain again. And so we look, do you see a radical? No. Do you see a fraction? Yes. Do you see a variable in the denominator? No, which means there's no restrictions. And the reason why there's no restrictions is because there's no variable in the denominator. So since we did our domain check number 1 and number 2, we are now ready to write the domain of the overall problem. Again, I suggest we look at the number line. Domain check number 1 says x cannot equal 1/7. Well, 1/7 is a fraction value that lives between 0 and 1. So I will place an open circle to represent where 1/7 lives on the number line. Now domain check number 2 says there's no restrictions, which means there's no extra values that need to be taken out of the domain, which means we can shade to the left of 1/7 and we can shade to the right of 1/7. And so now that we can see our number line, we can confidently write our interval notation as negative infinity, comma 1/7, parentheses, union, parentheses, 1/7 to infinity. Example 5. Given f of x equals 6x plus 5, g of x equals square root x, find f composed of g of x, g composed of f of x, and their domains. So let's look at f composed of g first. Again, because you see the circle for composition, you must rewrite it as f composed of g of x. On the inside, we see the g of x function, which means we put a square root of x on the inside. Since we've introduced a function, we must first check for domain. Do you see a fraction? No. Do you see a radical of even index? Yes, which means we take the radicand, or whatever is under the radical, and say it must be greater than or equal to 0. And in this case, we would write it as x is greater than or equal to 0. Since x is already isolated, we are ready to go ahead and continue with our composition. Because it says f composed of square root x, that means we look at the f function, and every time you see x, you put parentheses. Inside the parentheses, we plug in the square root of x. From here, we follow gems, but we have no grouping, no exponents. We do have multiplication because the 6 is touching the parenthesis, and so 6 times square root x, well, can that be multiplied? Yes. The 6 will remain on the outside, the x will remain under the radical, and so we have 6 square root x plus 5. The last part of GEMS is addition subtraction, but we do not have any like terms, so that is your final answer. Since that's our final answer, we're ready to check our domain again. So we look, do you see any fractions? No. How about radicals? Yes. So we only look at the part under the radical and we say that has to be greater than or equal to 0. Well, in this case, that would be x has to be greater than or equal to 0. And since x is already by itself, we have solved for the domain for check number 2. Now we must solve for the domain of the whole entire composition. And to help us, we need to draw a number line. By coincidence, they both end up being x is greater than or equal to 0. So in other words, something important happens at 0. Now, what values are greater than 0? Values to the left or to the right? Well, to the right are greater values, so we shade to the right of 0 on the number line. Now the question is, do we include 0? Yes, which means we will put a bracket. And so now that we can see the number line, we're ready for interval notation. Bracket 0, infinity. Now we're ready to look at G composed of F. Again, because we see that circle, we need to take the time to rewrite this as G composed of f of x. We start with the inside function, which is f of x, or 6x plus 5. Since we introduced a new function, we have to check our domain. Do you see a fraction? No. Do you see a radical? No. Which means we have no restrictions. All because there was no fraction and no radical, which means there's no problems, no numbers have been removed from the domain. So we're ready to continue with our composition. There's nothing we can do inside the grouping, so now we look at the outside function, which is the g function. The g function is square root of x. Well, every time you see x, you put parentheses. So we have a square root. Now what value do we plug in for x? Well, that would be 6x plus 5. So we've plugged the function of f into the g function. Now we're ready to simplify if possible. Is there anything we can do inside the grouping? No. Any exponents? No. Any multiplication? No. Notice there's nothing in front of the parenthesis, which means there's nothing to distribute, so there's no need for the parentheses anymore. Is there any addition or subtraction that we can perform? No, because 6x plus 5 are not like terms, so this is the result of your composition, the square root of 6x plus 5. Since this is the result of our composition, we have to check our domain. So we look. Do you see a fraction? No. Do you see a radical? Yes. So again, we take whatever the radicand is and say it must be greater than or equal to 0. For us, that would be 6x plus 5 must be greater than or equal to 0. And now we need to solve for x. Our first step would be to subtract 5 on both sides. And then we need to divide both the left side and the right side by 6. And we find x is greater than or equal to negative 5/6. Since we've identified our domain check number 1 and 2, we're now ready to identify the overall domain of the composition. Again, I suggest you draw a number line. The first domain check says there was no restriction, so we get to keep all the numbers. But domain check number 2 has a problem. It says something happens at negative 5/6. Well, negative 5/6 exists close to negative 1 on the number line. Now, what values would be considered larger than negative 5/6? Well, that would be the values to the right. So we would shade to the right of negative 5/6 on the number line. Now we must decide, do we include negative 5/6? And the answer is yes, which means we would have a bracket. And so now that we see the shading on the number line, we're ready for our interval notation. It would be bracket negative 5/6, comma, infinity